Now, coming to the properties of electrical field. So, electrical conductivity is one parameter that varies when the size of the particle changed. So, in ceramics, for example, ceramic in the sense like it's a brick kind of material, hard material. So, in the ceramics, electrical conductivity increases as nanoparticle size decreases. So, as the nanoparticle size decreases, that means that thickness is reduced, conductivity increases. That is one typical characteristics we can observe in ceramics. Similarly, in metals. So, electrical conductivity decreases as nanoparticle size decreases. So, as nanoparticle size decreases, the thickness of the material reduces. So, particle size is reduces in the sense the vicinity of atom to atom reduces. So, that is what the conductivity reduces. Similarly, electrical properties changes with nanoparticle size, and there are four cases maybe like one surface structure, their property of nanomaterial behaves differently, change of electronic structure, quantum transport, and effect of microstructure. So these are four properties in which nanoparticles or nanomaterials have greater impact. Now coming to uh, the other slide, that is mechanical properties, in which we have to concentrate on strength, plasticity, hardness, toughness, ductility, and rigidity. So electrical properties are related to like conductivity, whereas when it comes to mechanical, it's like strength, plasticity, hardness, toughness. So nanomaterial shows excellent mechanical properties. So that is external mechanical properties because of the size, basically their volume, fit into system, then surface, quantum effect of nanoparticles and all. So as nanoparticle size increases, mechanical properties decreases. So how nano how nano the particle that will be used in the system, that mechanical property will improve. So size should be reduced has to increase the properties of the mechanical systems, right? Then addition, the amount, ratio, and nanoparticle size have a certain impact on the mechanical properties of nanocomposites. So, for example, the fracture toughness, flexible strength, and hardness of a ceramic composite can be better promoted by adding nano TIN, titanium nitrate, than by adding nano Al2O3 to the matrix. These are chemical compounds like upon adding two different chemical compounds, so the material brittleness or toughness changes. So according to requirement or according to application, that can be made either hard material or that can be flexible material. So by adding different chemical compounds. Okay, so and in this slide you can see that magnetic properties. So we have so far we have seen electrical properties, mechanical properties, and then now magnetic properties. So when it comes to magnetic nanoparticles that are ranging between 1 nanometer to 100 nanometer, generally display super paramagnetic properties. So it may increase by adding external magnet. So generally, if you observe that even in the sand also, when you keep a large magnet around it, small duct particles or like black spots will be attached to the big magnet. So that means the grain kind of magnetic material shows very, what do you say? Um, Effectively will come and attach to the big magnet. So their properties are super paramagnetic materials. So nanomaterials are more magnetic than bulk materials. That's what. So when it comes to bulk magnet, it may be hardly move to other particle to attract, whereas tiny particles are very easy to move and to revolve around any kind of other magnet. So easily they can be get varied from the required position. from one point to other point. So nanomaterials are more magnetic than bulk materials. Even non-magnetic solid becomes magnetic when reduced to nanoscale. So even if it is non-magnetic material, but when it comes to cut it to the nano level, it shows or it exhibits little magnetic behavior. So as an example, sodium and potassium behaves like a paramagnetic at bulk, but a ferromagnetic at the nanoscale again. Ferrite, cobalt, nickel show a ferromagnetic behavior at bulk, whereas super paramagnetic at nano size. So this is one small graph is represented here. Magnetic properties nanoparticles. So magnetization, so this nanoparticle size, when it improves or when it I mean to say in the tiny mode when it is improves, that means as particle becomes very less and less, during that time the right hand side curve you can observe that it is raising, the magnetization part is rising. Okay, so when it comes to left hand side, x-axis left hand side, the magnetic nanoparticle size is little bit more. So their magnetization is done little, and finally it is becoming constant as as it reaches to some higher level of magnetization. Beyond that, it will not exhibit any other separate or different magnetization. So once it is get saturated with the amount of magnetization, how much it is absorbed, with that it will exhibit throughout the nanoparticle. So that is one characteristics we can observe under magnetic properties. Now let us see melting point, chemical under chemical properties, melting points. So nanoparticles has usually low melting points and reduced to lattice constant because they are of very tiny. So melting point is very compared to bulk scale materials. Their melting point is very um, uh, low, very low. So as well as lattice constant, they will come to constant at lattice due to change of surface energy to volume energy ratio. So decrease the size of the nanoparticles and the melting point decreases. So surface energy increases with the increasing surface area. And actually, this is in contrast, bulk material needs more energy or more power to melt, or for nano, it is not that much required. So, low melting point in the sense, the melting point is less required here. So, size of effect of nanoparticle melting point decreases. If you observe that this is a bigger circle at 200 amps diameter, and then this is 150 and this is 100. Then when it comes to dot, like at 50, between 0 to 50 diameter, it is showing like a dot. Now it is the temperature on the y-axis, for the bigger circle it is 1300 Kelvin, whereas when it comes to a small particle 500 Kelvin. So melting point is less, that means reduced inversely as the nanoparticle small size is coming. So melting point may be lower or higher for nanoparticles depending on the strength of the interaction between the particles and matrix. So it is not common to all kind of nanomaterials. That is the point where some kind of nanoparticles takes low melting point. And now coming to the next properties, like uh, uh, this is reactivity and stability. So more reactive than bulk materials. Nanomaterials are more reactive, as we already discussed in magnetic properties and all. So they are as because of tiny size and more fast active materials, so more reactive than bulk materials because of high surface area or surface energy. So when we break the bond to make nano size, so that means when the bulk size, if you observe that they are atomically bonded together, but when they become tiny, nanoparticles are tiny, so their energy each will get its equivalent energy. So the bond, the break of bond will give them more suitable to react with another kind of material. So it get high surface energy. The surface area reduces, size of the particle reduces. And then reactivity increases. In contrast, reactivity increases and surface area increases. So nanomaterials are extensively unstable. So generally, the tiny particles available, see if you observe that they will be available on the surface of the material. So reactivity reduces and the stability increases. In contrast, reactivity increases, the stability decreases. So these are the important features or points we can observe under nano materials. And then coming to the next slides. These are like size of effect of nanomaterials. So just in the previous slide, we have seen surface effect, that is size of the particle available on the surface, of the material. So quantum confinement effect. This is generally we can call it as nanomaterial quantum confinement effect. So in the graph, you can observe that the bulk material with the higher group of elements, it is at 100 nano, and then 60 nano a little bit lower, and then 20 nano, 40 nano. So their disposition is very position. That means the movement or the confinement will be very, what do I say? Nanomaterials is different compared to bulk materials. Dispositions is very high. So coming to the particle size in the right hand side, energy. Particle size is when the size of the particle is higher, their bond energy, that means mobility level to stable level. That means nothing but valence band to conduction band energy levels are low when the particle size is high. That's what particle size is high, they will be more stable as the internal energy gap is very less. But when it comes to coming to the particle size of nano, so they will be between level of energy band, that is valence band to conduction band, and they will be very active to move either into conduction band or either into valence band. Their energy, by supplying an additional of energy, a little bit of amount energy is sufficient for them to come out of its bond. So here, that is what in the previous slide we have seen. Reactivity, how reactivity is less when the stability is more, or those two are contrast, right? So reactivity is less if the energy is high, or energy is less, reactivity is high. Like that, it is shown different materials like metal, bulk semiconductor, and then a semiconductor, single molecule, the reactivity energy graph here.